Hello, 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 everybody, and welcome back. If you're watching this, then you missed not day one, but day two of Computer Science Principles, week two. And we are going to go ahead and go through what you missed. If you're watching this and you saw the lecture, then you're going to see some review. Here we go. We're going to be looking into how that circle, square, triangle activity we did on day one really leads us to understanding number systems. We're going to discuss the basics of what makes a number system work and how we can have different bases other than the usual 10 that we're used to. And we're going to take a look at a assignment that's going to be due the Tuesday of next week. Farther tonight, that is today, the 10th, your first assignment that has to do with number systems is due. 01.01.01 square circle triangle. It's posted on my MCPS. Please make sure you have that turned in by midnight. All right, our objectives are that you can deduce how to represent a number in a base different from 10. So this could be any base, and we'll talk about kind of the fundamentals of how you get there. You won't quite be there today, but we will get there by the first day of next week. And we're going to do basic conversions from decimal to binary. You should be able to do that after this lecture. Let's go ahead and get into it. For our warm-up, what I asked you guys to do is to think of a number system that is prevalent in our society that is not base 10. An answer for this that came to my head was time. Time is sexagesimal, meaning it's base 60. Very different from, our base 10, but we are very used to it. We don't question it. And why is it here? Well, the ancient Babylonians actually used the base 60 number system, and we've inherited their way of keeping time. Kind of interesting. That's just a little bit of trivia. Moving on, let's talk about that circle, square, triangle activity we started on last time. So why are we doing this? Let's kind of walk it through to its conclusion. If you have one spot to put a shape, and I gave you 3 shapes to choose from, how many different shapes could you make, or different patterns? Well, in this case, you would only be able to make 3, right? You could either put a circle, a triangle, or square in that spot. Very simple. Now let's go ahead and expand that idea to 2 patterns. Now, how could we do this? There's different ways to order these shapes, the 2 pattern shapes, but I'm going to use a very systematic approach that you guys are really going to see is very, very useful if we want to keep going past 2 shapes patterns. So for 2 shape patterns, what I'm going to do is I'm going to take my already agreed upon pattern of 3 shapes here, circle, triangle, square. I'm going to copy it 3 times. Now the reason for doing so is I want to put each one of my shapes in front of each of these groups. So I'm going to place circles, I'm going to place triangles, and then I'm going to place squares all in front of each of those groups. Now hopefully you see that this forms 9 unique pairings, and this exhausts all possibilities. So, okay, that's pretty cool. Now let's say I want to go to 3 shape patterns. We would get 27 different possibilities, and we could get those by taking this whole thing for 2 shape patterns, copying it down 3 times, and then sticking a circle, a triangle, and a square in front of each of those. So this is all the possible 27 shape patterns that you could get. All right, we've done it, and hopefully you guys can see that I could keep doing this as much as I wanted. If I wanted to go to my 4 shape patterns, I could take all of these, copy them 3 times, because I have 3 shapes, and put each of the unique shapes in front of all of those groupings. And I could keep doing this infinitely to get an infinite number of patterns, so long as I keep adding, well, an extra spot. We're going to call that extra spot in a second an extra place value. This is really a beginnings of a number system. So if I was to number these, I could say, well, let's make a mapping, and I'm going to put a number to each of these, and I could count using them. Now, in a society that we live in, we decided we're not going to use circles, triangles, and squares. We made a different decision. We decided to use 10 Arabic numerals instead. So let's take a look at that. What if we had 10 shapes? So instead of circle, triangle, square, we use 10 unique shapes. Now, that's a lot of shapes to keep track of, so it might be a little hard. So let's see if you guys can remember 10 shapes instead of just 3. It's going to be tricky. These are difficult shapes. So here they are. I mean, I don't know. This is asking a lot of you guys. They look kind of similar. Can you keep track of all of them? I don't know. The point is, these are just shapes, and we've assigned them a certain meaning. Notice that there is a 0 here. They'll have 10 shapes. One of them is always going to be a 0 in any number system. No matter what number system you work with, you must have a 0. Otherwise, there's no way to keep to keep track of your place value. Without keeping track of your place value, you will not be able to count. So this is vital. All right, let's keep going here. So if we were to look at our 10 shapes here, every time we run out of shapes to go through in a certain place, we revert back to the beginning, back to 0, and we count 1 up in the next spot. So we do this without thinking when we use our decimal system. This becomes a 0, this becomes a 0, this becomes a 1. That's very, very natural to us. It works the same way in other base number systems, but it's going to look a little different. So let's go ahead and think about this. If we have 10 possible numbers, well, we have 10 possibilities if we have just one slot to put them in. We'd have 100 possibilities if we had 2 slots, and we'd have 1,000 possibilities with 3 slots. Notice each time the number of options goes up by 10 times. So 10 times 10 is 100, times 10 is 1,000, and so on and so forth. In our system, we had 3 possible options. So if we were to go to the next spot, we would have 3 times 3, or 9 possible options, 27, and so on and so forth. It would increase by a factor of 3 every time. So let's see one more thing before we put it all together. If you were to write out the number 4017, what does this really mean? Well, if you go back to kind of your kindergarten experience, you will remember that what we really mean is there's 7 ones, there's 1 10, no 100s, and 4 1000s. And we could break these out and multiply them by their respective actual meanings within this whole number and add them up to get the total. Now, we represent that total the same way, so there's really little point in doing this, but you're going to see how this kind of compares to other number systems if we want to convert them into decimal. This is kind of the process we will follow. All right, so where's this heading? We're going to be using binary in this class. Binary is a number system that only has 2 symbols. It is used by most computers and, in fact, is incredibly useful for them because if you want to represent numbers within an electric system, you could use something being on to represent a 1 and something being off to represent a 0. That's very, very easy to do. So we have 2 shapes. We could use circles and squares to represent them, but we've decided that's a little tricky. So instead, let's use something we're more familiar with. We'll use a 0 and a 1. 1 will stand for on, 0 will stand for off. So let's do the same thing we did with our 3 shapes. Let's think about how many possible options there are, depending on how many place values you have. If we have just 1 place value, well, it's either on or off. There are 2 possibilities. For 2 place values, we double the number of options. Now you have 4 possible things that you could create using these 2 spots. If you go to 3, you have 8, 16, 32, 64, and so on and so forth. Each new place value doubles the number of options that we have. So let's try the same thing we did earlier with 417, or 4017, but this time we're going to use this number, and I'm going to tell you that this is in base 2 instead of base 10. So what does that mean? Well, that means we need to think about it differently. This does not stand for numbers of 1s from 0 to 9, but rather it stands for just how many 1s we have. We have 1 1. This stands for how many 2s we have. We have none. There are 0 2s. Each place value, remember, doubles. So the next one will be double of the previous. This is how many 4s, and this is how many 8s we have. So altogether, we can break these up and add them up. We have 8 plus 4 plus 1 gives us 13. Another thing to note is any number system is characterized by its base being taken to a power in order to figure out what place values mean. So this first one is 2 to the power of 0, which gives us 1. This is 2 to the power of 1, or 2, 2 to the power of 2, or 4, 2 to the power of 3, 2 to the power of 4, and so on and so forth. And you could keep going infinitely if you'd like. You can write as many leading zeros as you want to here, and they mean nothing, similarly to how base 10 works. All right, congratulations. You can figure out what powers of 2 we need, and we can add them together if we take a binary number. So in binary, we often want to look at something called a byte. Each little 0 or 1 is going to be called a bit. A bit is just the smallest piece of information we can have. If you take 8 bits together, you form a byte. And you may have heard of bytes when you talk about storing things in computers, like storing a kilobyte of information or a megabyte. Well, when we refer to those things, we're talking about thousands or millions of these little guys, little 8 sets of bits. So if we were to write some numbers underneath here for zeros and ones, we could figure out, for instance, what this number represents in base 10, our regular number system. So if I was to tell you 00101001 in base 2, what is that in base 10? Well, it's just 32 plus 8 plus 1, or 41. That is the answer. Any number system has to have the idea of 0, it has to have place values, and it has to have at least 2 symbols. There is a tool called the Flippy-Do. You guys can find this tool on My and CPS underneath Modules. And I've given you 2 options. There's a physical one, and there is a digital one. Please refer to the digital one if you weren't in class, and you'll be able to figure out how to work it just by playing around with it. This is a tool to help you figure out how to convert numbers from binary to decimal and the other way around. So what you could do is you could put in a decimal number in here, such as 52, and then the tool will walk you through what it would look like in binary. So you want to look for the largest number that fits inside 52 out of this row up here, and you want to flip that bit on. So in this case, I would flip 32 on. I would keep going. 16 fits into the remainder of 20. I would keep going. 8 does not fit into 4, so I would stop, and I would select 4. So once these 2 numbers match, I have succeeded. And you can do the same thing to go the other way. Simply check the numbers you need to, and then you will be able to add them up here to figure out the decimal number. If that is not clear, please send me an email. I'll be happy to work with you individually. Lastly, we did start or demonstrate the next activity, which is going to be due the Tuesday of next week. It is posted up, and it'll be actually titled 010401 Binary Practice. That is all I have for you today. I hope you get familiar with binary numbers, and please, once again, email me if you have any questions or concerns. Thank you very much.